For the second part of the Markov chain, I want to return to a problem we saw in the first part. We saw a stochastic matrix, a 2 by 2, again where the column vectors are probability vectors that add to 1. This is what we call our initial state vector. We can sometimes give it a x sub 0 as like the beginning 1. And if you remember what we did, we multiplied this out, and just a quick show on my calculator. I already have it set up. Let me hit enter 3 times, recalling the first 3 vectors in this chain. And 3. And we stopped here because this was just the setup, and we saw that what's happening here is this same matrix keeps starting with this initial vector, produces an output vector, which becomes the next input, which produces this one, which becomes the next input, and there comes this chain. Now, something we might speculate on is we can see that these vectors are changing on us. Interesting, if you just look at just the top input, 0.5 jumps to 0.65. Interesting, it comes back down. Because I already have it in my calculator, let's notice something. Let's just watch this top number, and the bottom adjust accordingly. So it went up, it went back down to 605, back up to 618, down a little to 614. But it's interesting that my top input, it's kind of hovering around the 6.1 number, but they are changing each time. Well, let's just go nuts. I'm just going to keep hitting enter and watch what we notice here is that it didn't take long for my first entries to pretty much settle in on 0.6153, 3846. Now, let's see how far we go until my numbers don't change at all. And it looks like we're there. I can keep hitting enter right now, and it looks like my input vector is my output vector. And I can do this all day, and nothing's going to budge from here on out. So let me just capture the first 5 digits. Call that good. So 61538 and 38462. Well, it settled in on a final vector here, and that's when that happens. That's called the steady state vector. There's a sweet spot where the vector input matches the output, and that's a pretty important place to be. So the steady state vector. All right. Well, it's nice to have technology that can find that just by a few button hits, but of course we are math people, and we want to know how can you just find that without having to just hit enter many times. So watch this. It starts with the idea of what we've been doing here. If I have some generic square matrix times some initial vector 0, what do we want that to be? If it never changes, I want my output to be that exact same vector. So I want my what would we settle on? So my steady state vector becomes the output. So let's just do a little bit of algebra on this. Let's bring everybody to one side. So we know we've got this already here minus this vector. So again, remember, what is this object? A matrix times a vector is a vector. 2 vectors subtract is another vector, but when I move it over, it's the 0 vector. Now, to make these guys talk even better, let's bring in the identity matrix on this guy. And again, multiplying a vector times an identity matrix doesn't change it at all, so we didn't do anything. This just gives us an opportunity to factor out that vector, leaving p minus I times that steady state vector equals the 0 vector. So we still have the structure we've come to know and love in this class. I have a matrix times a vector equals vector. In a special case, it's the 0 vector. Let's take a look at this. What is p minus I? Well, in this problem, it was the 0.5, 0.5, 0.8, 0.2 minus my identity. So remember, that's just some big matrix. Here's the rest. So let's go ahead and subtract that over here. What do I have then? 0.5 minus 1 is negative 0.5. 0.8 minus 0 stays 0.8. 0.5 minus 0 stays 0.5. 0.2 minus 1 becomes negative 0.8. And here's the equation we're going to solve. This matrix equation, interesting. It's a homogeneous system. We could think of it as that. We know there's one solution, the trivial solution, but that's not interesting. Yes, if you always start with the 0 vector, you always end up with a 0 vector. I'm interested in something else. So we hope there's some free variables in here, and I think we can see that's going to happen. If I'll just jump to a row-reduced version of this. If we do, well, clearly if you add top to bottom, you got a row of zeros, and you're always going to need that. If I divide through then by negative 0.5, I get a positive 1 here and a negative 8/5 here. Okay. Well, we know what the rest of this is. Again, I'm trying to solve this, this matrix equation. I think I'm going to call out my two variables, x1, x2. There's my free one, and x1 is now 8/5 of x1. We know from here, whoops, that's x2, that's my free variable. Let's unpack the x2, leaving the vector 8/5, 1. Now, normally we could be done and call that good, but let's clean that up a bit. Let me bring this back down over here and say, is this the solution? The answer is yes, but so is any scaled version of this. So first of all, I like to get whole numbers, some integers here. So let's multiply this by 5, and that gives me 8/5. But my final steady state vector, remember, one of the conditions has to be non-negative entries that add to 1. Well, that's not adding to 1, it's add to 13. So here's a clever trick. We're going to scale this by multiplying by a fraction. 8 plus 5 is 13, so what if I multiply both by 1/13, giving us 8/13, 5/13. What do I like about this? Well, I have there's my steady state vector that we solved for. These add to 1, and I'll let you check. 8 divided by 13, yes, is 0.615. 5/13 is 384. Pretty cool. So we did it with just rough and dirty technology, got an answer pretty quick. This is the slick algebraic form. Let's do that one more time. All right, last example, let's start with stochastic matrix. How do I know that? All of the column entries add to 1. So let's say the entire question is, so given this stochastic matrix, another term I like, I like the feel of it. It's sometimes I've heard it called the migration matrix. And if you think of what's happening, remember you're taking a certain state given on, let's say, on a given day, and on the next day it either stays there or it migrates to a different position. In my last video, we talked about weather being good and different or bad, and so from one day to the next it could stay or it could switch. And so I like that term migration instead of stochastic. So just know that. What if we were, though, given this migration matrix, can we identify the steady state vector? That's all I want. what inputs wouldn't change if they were migrated by this matrix. And we're going to, what we just learned, the first thing we're going to do is, let's call that matrix P. And so I need to first get this. We're going to take P minus I. And so imagine there's a identity matrix 3 by 3 sitting next to this. Let's see if we can pull that off. 0.3 minus 1, negative 0.7. The next, you're subtracting 0, so those don't change. Same with the 0. The next one, 0.3 minus 1. There's another negative 0.7. Stays the same, stays the same, stays the same. And then finally, 0.6 minus 1 is negative 0.4. Now, I'm not showing the full equation that I had before, but the technique of what's going to happen next is, remember, this is part of a matrix equation. It's homogeneous, and I'm trying to find the non-trivial solutions to that. And we are going to, again, just trust me on my calculator. Actually, I want you to see something real quick. So if you'll indulge me real quick, I want to make sure you're aware of this move in our machines. All right, quick scan. Oop, glad I caught that. That should be a negative 0.4. Good. Yep. 0.3. Anything else? Mavis. Good, good, good. All right. So we're back to row reducing that dude, and blah, yikes. What's happening here? Just make sure you know that there is a quick conversion button that's going to make that look cleaner. Under math, choose number 1 for convert to fraction, and I can work with that much better. All right, so let's return to this. We've got a 1, 0, 0, 0, 1, 0, and the fractions negative 12 49ths, negative 4 sevenths, and 0. Remember, you're going to want a free variable every time. That's where we're going to get our solution. So here we go. x3, it is my free one. x2 then would be 4 sevenths. x3, 12 49ths. x3, let's unpack x3, leaving my first solution as this vector. Let's again, let's convert it all to clean integers. So how about we scale this by what would be a good multiplier? How about 49? And so that becomes next 12, 28, and 49. So better than the last. Not a fan of fractions, so this is good. But remember, this column vector has to add up to 1. And so let's add these together. What is that? It looks like it adds up to 81. So my last thing is let's scale, I'm sorry, 89. Let's scale by 1/89. So my final steady state vector, 12/89, 28, and 49/89. So just be aware in your online homework, sometimes it may ask for the fraction, it may ask for decimals to a certain second or third place, and I think that's good for our second example.